And away we go. All right. Our main objective today is dealing with adding and subtracting fractions. I did want to make sure, I don't know if you just saw the email I posted, or the message I posted in My Open Math. I was checking yesterday's video, make sure. All right, good. Christina's joining. Hello, Christina. I was checking yesterday's video just to see how it looked, and the post all right. It's a good thing I did. I watched it for a while and realized, oh, I made a mistake that I do once in a while, but I need to clarify it. Boy, you know, you hate it when your teacher makes a mistake. You count on us to get things right. And really the point is I use the words positive and negative when I should have been saying even and odd. And maybe you can see how it's easy to sort of fall in that trap. I was talking about these expressions like this, and I meant to make the point that the difference is most, you know, and the difference between that and that. I meant to make the point that the difference is most important or noticeable when the exponent is an even number, and I said positive. Well, they're all positive exponents. There are such things as negative exponents, but we don't deal with them in this class. I think by the time you get to Math 95, you figure out what those are all about. But my point here was, if it's an even exponent, well, here you get an even number of negative signs, which results in a positive value. Here you have an even exponent, but you apply the negative sign afterwards. So, you know, this is the one that's a negative 16, and this is the one that's a positive 16. You kind of recall that presentation yesterday. Now this one, this is an odd number of negative signs, so that will be a negative number. So that one's going to be negative 8. This one is saying find 2 cubed, and then apply the negative. So it's going to be negative also, but that's what I was saying. It's for a different reason, because this had a odd number of negative signs, and this one applied a negative after the fact. So I mixed up the words even, odd, and positive, negative. And I hope that didn't mess anybody up too much. Nobody caught it yesterday, as I said, as I was presenting it. Or maybe you were wondering what he was talking about. But well, I hope that's okay or clear enough, or be sure to ask me more questions if that's confusing. But that is sort of that important notation to understand the difference between those two when we run into it. Okay. How about other stuff that you might have run into in homework? Any issues that you want to, or questions you want to ask before I get started? In 1.6, adding and subtracting fractions. You know, in all seriousness, I appreciate, I mentioned, you know, Sasha posted yesterday, I believe, a picture from another source, just basically explaining, you know, same signs, you get a positive result, negative sign, you get a, let's see, opposite signs, you get a negative result. Okay, raining here this morning, come on. And I hope nobody took it the wrong way, but I wanted to point out that we're going to want to interpret that as a variable in the very near future. We can't really use that arithmetic multiplication x in algebra. It gets too confusing. Is that a variable, or does that mean multiply? So, you know, if in that example that she presented for us, this was supposed to mean -2 times -5. The way we would prefer to see that, of course, you don't even need the parentheses on the first number, but just put them either side by side to mean you're multiplying them together, or if you really like it, you know, put the dot in there. But that negative sign needs to be wrapped up in parentheses to, you know, say it's attached to that 5, and it's not a subtraction sign. So just addressing that again. But again, thank you, Sasha. And if you find things that you think are helpful, yes, please do. Please post them. And hopefully I won't pick on anybody too much, but you know, I do want to talk about what's the convention, the way we prefer to see it. So just addressing that a little bit. Well, on to adding and subtracting fractions. All right, multiplying and dividing. I was hoping maybe that seemed like a fairly straightforward process. Multiplying numerators, multiplying denominators together, reducing to lowest terms, finding common factors to cancel. Division is always flip over the one after the division side, multiply by its reciprocal, turn it into a multiplication problem. Well, addition, we run into, you know, issues of, can we put these apples and oranges together? So just a quick drawing here. That's supposed to look like 4 evenly sized pieces, and that's supposed to look like 3 equal sized pieces. Each one of these would be a fourth, and each one of these would be a third. So if I want to add those together, how much do I have? Well, we have different size pieces, and it's like the apples and oranges. We can't just, it's not 1/7. You can't just add the denominators. Sevenths would actually be smaller pieces. So we have to come up with what we call a common denominator. We need to break these all up into the same size pieces. And so we have to talk about doing that today. But we start with, if they are the same size pieces, that's kind of the easy thing, right? If I have 2/3 plus 4/3, oh, let's make it, I'm going to make it an odd number here, okay? If I have a bunch of pieces that are the same size, basically the denominator describes the size or how many pieces your whole is divided into. If I have a bunch of pieces the same size, well, then I can just add the numerator values and determine how many pieces of that size I have. They're still going to be thirds. Once you come up with the denominator that works for adding them together or subtracting, you don't change your denominator, except maybe at the last step if you have to simplify that fraction, lowest terms. But now I have 5 plus 2, I have 7/3. Since they were the same size pieces, I just get to add the tops together. Same would apply to a subtraction problem. I have halves. This is saying I have 9 halves, and I'm going to subtract 4 halves. How many halves do I have left? There's still going to be halves, but 9 minus 4 means I have 5 of those halves. If you've got the same denominator, keep that denominator, add or subtract. Now, there's nothing in the addition or subtraction process that guarantees you're going to end up with a lowest terms fraction. You recall yesterday we were multiplying, we might have been able to do some canceling before we multiplied and get pretty close to having lowest terms fraction at the end if we found all those factors. Well, there's nothing that guarantees this is lowest terms. I just really do have to look at it now and say, oh, did it happen to add up to something I can reduce? Now I made up a couple examples where it can't be reduced any further. So no problem in these 2 examples. Also notice within these examples, I've built what are called improper fractions. The numerator is larger than the denominator, means it's a value greater than 1 whole, right? It's 3/3 plus 2/3, a whole plus a couple more. In algebra, we don't almost ever use mixed numbers. I can't imagine actually you'll be ever asked to present a mixed number answer. It won't be wrong for a final answer. Sometimes in a certain application, it might be easier to say 1½ cups rather than 3/2 cups or something like that. But an improper fraction is usually good enough. And in fact, it's preferred if you were working with, you know, that number with several other operations around it. Okay, so don't worry about improper fractions. That's actually usually preferable. All right, so, and of course we could mix up You know, some order of operations kinds of issues here. Here are three fractions that I'm being asked to combine using addition and subtraction. They all have the denominator 9, so they are all the same size pieces. So I really can kind of think of this as 2 plus -4 minus 7 all over 9, right? I'm going to come up with an answer that's a certain number of ninths. So I'm just dealing with the numerators now. 2 minus 4 gets me to -2, and minus 7 more would get me to -9. -9 ninths. Those are supposed to look like nines. Well, all right, so we have a negative number. It's just the result of them adding up. 9 divided by 9 just happens to simplify to 1, right? So lowest terms would really just be -1, or 1 over 1 is okay, but -1 that happened to turn into an integer value. Okay, so just if you've got the same denominators, you know, we can just work with the numerators, put them together. Okay, well, what if they don't have the same denominator? Back to my thirds and fourths is a, you know, simple small number first example. I need to add those two together, but I need them to be the same size pieces. In a sense, if you're thinking about my circle here, when I divide it into fourths, well, if I divide every one of those fourths into 3 more pieces, now I've got 12ths. And here, if I took my thirds and divided all the thirds into 4 more pieces, if I can do that, 1, 2, 3, 4. Well, that turned all those into 12ths. Oh, well, if I had 1/4, that's now 3/12. And if I had, where is it? 1/3, that's now 4/12. So I found a common multiple. What's the number? What's preferably the smallest number that both 4 and 3 divide into? A larger number that they both divide into. Usually, you know, everybody's, you know, you run across that situation. Well, I just multiply the two of them together and I'll get that common number. That is true, which is kind of what I did with this first example, right? Multiplied that one by 4, multiplied by 3 and multiplied that one by 4. Got to a common multiple. As the numbers get bigger and more complicated, we'd like to find the lowest common denominator. What's that smallest multiple, least common multiple? Anyway, so this one is the same. Here's an equivalent fraction. Notice the way, how would I get that? Once I decide what that denominator is going to be, I make an equivalent fraction with that denominator. How did I turn this into that? By multiplying both the top and the bottom by the same number. That's kind of a big deal there. You got to build an equivalent fraction, multiplying in a sense by 1 in this special form. 3/3 is a version of 1, right? Doesn't change it. This one I'm going to multiply by 4/4. However you want to put those dots in there. And I get to 4/12. So I built that equivalent fraction. That equivalent fraction, specifically, I was trying to get 12 in both of them. Now they have that common denominator. I can add them together. That means I have 7/12. 1/3 plus 1/4 is the same as 7/12. So again, this one, it just happened to be in lowest terms, no common factors to cancel. So that's the, you know, sort of like the, I want to say, easy first example. How we do that. Find a common multiple and then make equivalent fractions. All right. Now, here are two fractions I'm being asked to add. Now, the same process of coming up with a common denominator and performing the operation will apply if we're subtracting also. Adding or subtracting, we have to have the same size pieces. But here I have a 12 and here I have a 15. If I just multiply 12 times 15, I'm gonna get a real big number for common denominator. Kind of cumbersome to work with. We preferred, to find the lowest common denominator. Now I addressed this a little bit, this process a little bit the first day as I was talking about prime factorization or least common multiple. What's the smallest number, preferably, that both of these divide into? So we're looking for a multiple of those numbers and finding the common multiple. One way to do that is to just start with your number and start multiplying it times 1, times 2, times 3, times 4. Find the multiples, and you get a list. 1 times 12, 2 times 12, 3 times 12, 4 times 12, 5 times 12, 6 times 12, 7 times 12. I'm gonna stop and hope that I run into a multiple without having to go too much further. Same thing with 15 now, and I'm gonna keep going until I run into one of these numbers. So 1 times 15, 2 times 15, 3 times 15, 4 times 15, 60. 60 is a number that is a common multiple, and it was the first one I ran into. So both of these numbers divide into 60. So I'm going to use 60 as my common denominator. Back up here in a second and show the other process for coming up with that common multiple. So if I'm going to turn this one into 60 and this one into 60, what do I have to multiply 12 by to turn it into 60? So kind of got to go a little backwards, like 60 divided by 12, 5. I have to multiply 12 by 5 to get it to be 60. So if I'm doing that on the bottom, I have to do it on the top to build an equivalent fraction. 7 times 5 means I have 35 sixtieths. What did I multiply? And here I can figure out 1, 2, 3, 4, 5. That's how many multiples it took to get to 60. What did I multiply 15 by? 1, 2, 3, 4. 4 times 15. So if I multiply this by 4, I have to multiply that by 4. Build that equivalent fraction. 44. Now they're the same size pieces. I can add them together. How many 60ths? And I'm going to get 79. 79 60ths. I'm pretty sure 79 is a prime number, actually. You know, I do this enough that I'm kind of familiar with a lot of it, but I can see it's not an even number. It's not a multiple of 5. Remember, 7 plus 9 is 16. It means it's not divisible by 3. I'm pretty sure I'm pretty good here. You know, no common factor in there. I'm done. But my process there found a common multiple. Now there is a, I want to say, more methodical way, another way to do that, and that was related to the prime factors of those original numbers. See if I can work this still around what I've already got here. 12, let's say 2 times 6, and that's 2 times 3. So 12 equals 2 times 2 times 3. There's no other way to make a 12 without multiplying those 3 numbers together. Now you can say, oh, well, you could use a 6. Well, that's still just a 2 times 3. Those are the only prime factors that multiply together to get a 12. Similarly for 15, well, how about 3 and 5? Oh, that's it, 3 times 5. Those are the prime factors in 15. Now, if I'm going to come up with a common multiple, common denominator, it's got to have all the different prime factors that were present in either number and the largest number of any of them that occurred in either number. That last sentence, I always say, oh, it's kind of hard to make sure to say that clearly or have it make sense. But my least common multiple, in this case, it's going to be the denominator, is got to have 2s and 3s in it. And in order to be a number that's divisible by 12, it's got to have 2 2s. So I'm going to put an exponent up here. Now the 5 needs a 3 and a 5. Well, I've already got a 3. I don't need to duplicate it. This 1 3 will work to get me halfway to 15, right? But I also need a 5. This one's kind of nice the way it lines up, because I can say, see, there's the 12 and there's the 15. So I've got all the building blocks necessary to make a number that I can fit 12 into and I can fit 15 into. So now I've got all the factors I have to use. 4 times 3 is a 12 times 5, and we get to our 60. So if you break both numbers down into their prime factors, then you use all the different factors required and make sure if this one has 2 of something, then you need 2 of them. This one had 2 of something, you'd need 2 of that factor, and put them all together. We'll do that again.
Is that just like a second method to doing that? Or can we like use, I like the first method that we did the best.
Yeah, I think this one's a little, I want to say a little more abstract or technical or something. The first one, I would say you're not alone. Most students often like that first method. You know, it's like, well, yeah, I can just keep multiplying. You can imagine, gee, if it's really odd, awkward numbers, that could be a long, long list. Sometimes this could be a shorter method if the numbers are not closely related, you might say something like that. Okay? All right. So just going to keep doing a few more of these, huh? So this is all about the work necessary to get the common denominator. Once you've got the common denominator, well, then you can do the operation, put them together. Look okay? Yeah, good. My lighting's pretty good today. All right. Same problem, difficulty, right? Same thing we have to accomplish. All right, if you want to do the first technique, first method, let's see, 1 times 15, 2 times 15, 3 times 15, 4 times 15, 5 times 15. I'm going to stop. 1 times 20, 2 times 20, 3 times 20. Oh, how boring, it's a 60 again. Just by chance, first 2 examples. Common multiple, 60 is going to work for both of those. So again, boring, just by chance, I picked 2 examples where 60 is going to be this common denominator. Notice those were different numbers though to start than the last example. So what did I have to multiply by? 1, 2, 3, 4 to get to 60 there. 52, however you figure out, okay? And 1, 2, 3 had to multiply times 3. 3 times 7 is 21. 1 times 3, 4, 5, 51. So that's 51 sixtieths as a equivalent fraction and 52 sixtieths as an equivalent fraction. Now I can add them together. Looks like 103 sixtieths. That's good, I'm sure. Again, I think 103 is a prime number. We're just running into things that don't simplify, but I keep saying it. You do want to look at your last step. Can I reduce it now to lowest terms any further? The other technique. Okay, the other technique, again, 15 is a 3 times a 5, and 20, 4 times 5, so that's 2 times 2 times 5. And, well, it's going to be similar to the last one because it's got to have 2s and 3s and 5s. And this number requires 2 factors of 2. So again, well, there's my 4 times 5 gets me the 20, and there's the 3 times 5 gets me the 15. But those are all the prime factors I would need to build that lowest common denominator. Again, it was a 60. Just going to do it again, okay? Like, what's that problem doing on this paper here? All right, I'm changing this one from what the example looked like on my paper. That scares me sometimes. I hope I don't make anything too crazy out of it. Yeah, so. All right, so, oh, look at those denominators. Kind of messy, big numbers possibly. So now that's a negative and that's a negative, but we're adding 2 negatives. So I'm still going to get a negative. This is not negative times negative turns positive. This is negative and some more negative. We're going to get a more negative number, a larger negative out of this process probably. All right, so here we go. Try both techniques, okay? This little worries me. It's like I'm going to run out of it. I have to get my calculator perhaps. But 1 times 27, 2 times 27, and 27 is 54. 3 times 27 would be, I got to do it here just to be safe, 81. Oh, yeah, sure. I do that. And let's see, 4 times 27, 54, 54, 108. Let's see if maybe that's enough, okay? Now 1 times 36, 2 times 36, 72, 3 times 36, 3 times 6 is 18, 9, 10, oh good, 108. So the technique worked, didn't really have to go too long a list, but I could imagine you might have pulled out a calculator to actually start doing all those multiples. I did a little just, the scratch work. That works too. So 108 is the common denominator in this situation. Don't lose your negative signs. But to get to 108 here, I had to do 1, 2, 3, 4. Squeeze that in over here on this side because of that negative right now. So that was negative 28 over 108 plus. Now, 36, 1, 2, 3, we had to multiply by 3 to get there. Times 3, times 3. That's supposed to get to 108. But 3 times 35, 3 times 5 is 15, carrying my 1, I get 105. And that was also negative. Don't lose your negative signs. All right. That's the hard work, right? Found the common denominator, built the equivalent fractions. Now let's add those together, and it will be negative number of 108ths. 105 plus 28, stack it up or whatever, however you want to do that. 133. Now 108 is divisible by 3. 8 plus 1 is 9, but 3, 6, 7, that's not divisible by 3. I'm going to think I'm probably good. I'm probably done with that lowest terms. Now this one, you might have liked, not working with the big numbers, you might like that other technique. So just show you how that would work. Kind of do this for a while, side by side. 27 is what? 3 times 9, which is 3 times 3. 27 is actually 3 times 3 times 3. It's entirely built out of threes. And 36, well, let's see, how about 4 times 9? But that's 2 times 2 and 3 times 3. So 2 times 2 times 3 times 3. There are all the factors I need to build a 36 and all the factors I need to build a 27. Well, now I'm going to build my lowest common denominator, least common multiple. I usually call it at this point, but I'm going to need, it's just 2's and 3's. So I need 2's and 3's. What's the largest number of 2's required by either of the numbers? I need 2 2's to get some number that 36 will fit into. This one didn't need any 2's. Oh well. How many 3's? What's the largest number of 3's? 2 here, but 3 here. So I'm going to need 3 factors of 3 to be able to divide by 27. So there are the pieces that will get me my common denominator. Call it 4 times 27, and we got our 1 weight. So whether you like the multiple version or the prime factor version, sometimes they're just familiar enough and small enough. It's like, oh, I can see, I know what that small number they both fit into. 3 and 4, they both go to 12 or something like that. You don't need to do much work. If you know you're right, you're good, okay? And if by chance you actually come up with a larger denominator than the lowest common denominator, and you work the problem, it just means when you get to the end, you're really going to have to simplify. If you didn't use the lowest common denominator, then you can pretty much be sure you're going to have to simplify that final answer. You're going to have to reduce it to that lowest common denominator. There will be something you can cancel out. How are we doing here? Should I keep doing more of these kinds of examples, or can I go on to the next concept? How do you feel about this process? Thank you. Yeah. Okay, I'm going to, in interest of time, we want to try and get through everything in this section today. All right. So the next thing that we deal with in this section is referred to simplifying complex fractions. Where'd my good examples go? Here we go. All right. So first of all, just something like, what is a complex fraction? Well, it's a fraction built out of fractions. And I switch my pens here as this one's been open too long. That's supposed to look like the fraction 2/3 on top and the fraction 5/6 on the bottom. So it's a fraction that has fractions in both the numerator and denominator. It might just be one side, might be the other, it might be both, but that's what the definition of a complex fraction is. It has fractions in its inside of it someplace. Well, we need to, how do we approach this? Well, here's where we have to remember the fraction bar is a grouping symbol. So if there was any simplifying to do on top, we would do that first. And any simplifying to do on the bottom, we would do that first, just to get those two parts as compact as possible. And then the next thing is to recognize this means division. This is a division problem. This fraction is the same as 2/3 divided by 5/6. Right? Top number divided by the bottom number. We get to this, now we do what we did yesterday. We're going to turn this the division problem into a multiplication problem by inverting or using the reciprocal of the number after the division sign. Flip it over and turn it into multiplication. This is equal to 2/3 times reciprocal 6/5. I'm going to come back and kind of explain it from a different view in a second here. And now I'm in this position, I'm multiplying. You might save yourself a little time if you recognize, oh, I can divide these both by 3s. So this gets me to 4/5 would be my final answer. Why does this work? Imagine back up here, if I just, for some reason, if I choose to multiply the top and the bottom of any fraction by the same number, I'm building an equivalent fraction. No matter what I choose to multiply, if I multiply by 12 over 12, it's an equivalent fraction. Well, what if I specifically choose to multiply by the reciprocal of the denominator, top and bottom? What happens? Well, on the bottom, 6 and 6 cancel, and 5 and 5 cancel, and I get a 1. Nice number for a denominator now. On the top, though, I still have 2/3 times 6/5. But it's all over 1. So this, whoops, turns into that one, right? It turns into, I can drop the 1. It turns into that invert and multiply problem. That's kind of a way to justify that invert and multiply process. Why does it work? Well, it's because it's really a notational equivalent to this process of multiplying the top and the bottom of that kind of division by the same number. Anyway, that was a complex fraction, and it didn't need simplification in the numerator or in the denominator, so we just recognized it as a division problem and turned it into multiplying by reciprocal. Well, and so they get a little more trickier if there's more work to do to simplify them first. So here we go, we try that. And all right, order of operations stuff, really. All right, here is a fraction that is a complex fraction. It happens to have a fraction on the bottom. Now, just because that's really what makes it a complex fraction, is there's a fraction inside of it. If there were just a bunch of integers, it would just mean we had to simplify and turn it into a simple fraction, not complex. But eventually we're going to have something divided by this fraction. But we're going to simplify the numerator separately and the denominator separately. So I'm going to work this way, just save some space. We have no grouping there, but we have exponents. 2 cubed, not 6, but 2 times 2 times 2 is 8, plus 4 squared, 4 times 4, 16. And I'll go one step further here and say, okay, that's going to get us to 24. I mentioned yesterday we like to show steps vertically, but I'm saving board space. All right, 2/3 squared. Oh, we haven't put exponents on fractions before, but that just means 2/3 times 2/3. Square the top number, 4. Square the bottom number, 9. 2 times 2, 3 times 3. That is 4/9. So if you're applying an exponent to a fraction, it's like having the 2 on top and on the bottom. Okay, you could just deal with the numerator and denominator separately, just kind of like I did as a pullout over here. Or do this if you want to be sure. You don't line them all up, how many factors in a row. All right, so this carries over. So that's 24 divided by 4/9. So I have a whole number divided by a fraction. If I'm dividing by that fraction, I have to turn it into multiplication by using the reciprocal of that fraction. I'm going to make it look like fraction times fraction by putting a 1 there. Flip this over. Now I've turned it into the equivalent multiplication problem. Ready to do the multiplying? Anything I can cancel, save myself some work? Well, yeah, I can divide these two by 4s. All right, that's going to be nice. 1 times 1 just happens to be a 1. I'll show it, but at the last step, I usually just write the whole number. 6 times 9, and then 54. Math facts, right? Okay, so I would just write 54. Watch out, any of these problems might have a negative sign thrown in some places, like, oh, remember, carry your negative sign around. So there was some simplifying to do, both the numerator and denominator, before we were able to then interpret it like this division problem. I'll do one more of those. Oops. Definitely complex fraction. Fractions on top, fractions on the bottom, and both numerator and denominator need simplifying before we can turn it into a simple division problem. But look at those fractions. They don't have a common denominator. Is this one maybe easy enough? You can look at those two numbers. What's a good denominator? 2 times 2, just a 5. It's going to be 4 times 5. The 20 will be the common denominator. If you had to do 4, 8, 16, 20, or 5, 10, 15, 20 to get there, that's fine. But 20 is going to be the number that works as a common denominator. It just so happens that both the numerator and denominator have the same two numbers, and so 20 is going to work on the bottom also. That won't necessarily be the case all the time, but just this problem was designed with the same denominators all around, you might say. Okay, how do I turn this into 20? Multiply by 5. How do I turn that into 20? Multiply by 4. Do it at the top and bottom of both equivalent fractions. 15, 12. Okay. Similarly here, times 5, times 4. Excuse me, 5 and 8. Now finally, just to get to simple fractions, minus, so 3/20 over 5 plus 8, 13. Now I've got one fraction divided by one fraction, and I can interpret it as that division problem. If you really are comfortable with what you're doing and you just go right to the multiplication step by flipping over that denominator, that's okay if you are real confident in your process. You know what you're doing. So I'm going to turn this into a multiplication using the reciprocal. Well, they all had 20s, so those are going to go away. 1 and 1, right? So I have 3 times 1, 1 times 13, 3/13. That messy looking thing to start with is equivalent to 3/13 simplified. Hope that looks like a 3 there to you. Anyway, that's as messy, as tricky as I think we're going to try to get with that stuff. All right. Now, the last idea in our section here of adding and subtracting has to do with evaluating expressions that have fractions in them. Remember, we're working with just expressions. We're just simplifying or evaluating. If there's a variable, plug a number in and see what you get if you use that number. Still not solving anything, no equations. Although you notice I will say, I started here and that's equal to the next thing I'm doing, and that's equal to the next thing I'm doing. Sometimes mathematicians will show this first step is now equal to this next step, that equal to this next step. We're not really in the middle of solving an equation. We're just showing these things are equivalent. Let's say I've got x plus 3/4. Evaluate that expression if x is a negative 7/4 or if x is negative 4/5. Two problems in one, two different numbers to plug in for x and then see them simplify, see what you get. All right, so if x is a negative 7/4, I'm just replacing the x with that number. And the rest of the expression, see what you get. Oh, how nice, same denominators. So I'm gonna have a certain number of fourths, negative 7 plus 3, negative 4. Oh, I'll simplify that to a negative 1 because the 4's cancel each other out. Evaluating, plug the numbers in. How about if x happens to be a negative 4/5? All right, well, they don't have a common denominator. Notice these are added, they're not multiplying, they're not factors. I can't cancel those 4's or anything. You can't do that in an add or subtract problem, only if you're multiplying. So I need a common denominator. Oh, we just did one with 4's and 5's, 20. So I'm gonna say, I'm gonna get, this one's still a negative. I'm gonna get two fractions that have 20 as the denominator. Times 4, times 5. I'm going to get negative 16 and 15. So my answer will be a number of 20ths, negative 16 plus 15. I have a negative 1 left. I can write that negative there. I could put it out front. A couple common ways you'd see that. Negative 1/20. How about a couple more of those? At least one here. I guess if you run out of time, you gotta go, you gotta go. But how about 3ab squared? And a is a negative 2/3, and b is a negative 1/2. The nice thing about this one, it's multiply. So plug in those numbers. Here's the 3. The a is this fraction. It has a negative sign, so I'm going to put parentheses around it. And the b is a fraction with a negative sign and even an exponent. So I'm going to, now, I'm plugging in negative 1/2 for the b. The negative sign is part of the b. That's going to get squared. It needs to be inside the parentheses. The negative is part of what's being squared. Here's where that topic we started with today pops up. And in evaluating, it's part of b. It goes in, that's all b right there. Needs the parentheses because it's going to get squared. And now, let's see. I can, well, grouping symbols, not really other than holding the negative signs, but there is an exponent. So I'm going to square that fraction. 3 times negative 2/3. Negative times negative is going to be positive, right? Negative 1/2 times negative 1/2 is what I'm doing there. I'm going to get positive 1/4. There, I did that squaring. All right, this is like 3/1. I have 3 fractions in a row. I'm going to rewrite this so maybe it's a little clearer to see what I'm getting at. But these 3 numbers on top as factors, these on the bottom, I can do some simplifying before I multiply. Like I can cancel both these 3's, and I can cancel the 2 out of these. Now I'm ready to multiply. Positive, negative, positive. It is going to be a negative number. 1 times 1 times 1. 1 times 1 times 2. Oh, all that mess was just turned into -1/2. I want to put one more up there, although I don't have time. I'm going to just make up something and not work it out, okay? You might run into something in homework that looks like three terms, and here the variable is a square, this one's not, and then we'll say something like, let A be 1/3 or something like that. Well, I have to put that 1/3 in for all the A's. And it's going to get squared, so I'm putting it around parentheses. And here's 3 times that 1/3 and a -5. There's just plugging it into all the places that had A. No real grouping, but I'd have to square that, and then I go from there and simplify. So I just wanted to point out that one, and I think you'll see something like that in a homework problem. If you really get stuck, let me know. Send me the message. But we're out of time for today. Do your best. Of course, this is due. All this homework from this week is due by midnight on Monday. That means you can show up on Monday and ask questions if you are stumped on something. But I'll be checking email and Mom through the weekend and trying to reply to questions. My wife and I are actually going to vacation a little bit for Friday and Saturday, but I'll still be checking in to help you out. All right, so we've got to wrap it up. That's all for today. And good luck. Send me questions if you have trouble, okay? So
Thank you, Steve.
yes, see you Monday.
Thank you.